So we're starting chapter 6. Our first section is 6.1, rational expressions. So we're going to take a look at what they are, what we mean by non-permissible values, what equivalent rational expressions are, and how to simplify them. So rational expressions are algebraic fractions with a numerator and a denominator that are polynomials. And recall that polynomials are like monomials, binomials, trinomials, and so on. Some examples are 1 over x, so a monomial divided by a monomial, m over m plus 1, which is a monomial over a binomial, y squared minus 1 over y squared plus 2y plus 1, which is a binomial over a trinomial. Even expressions like x squared minus 4 are considered rational because their denominator is 1. To continue our discussion, we need to know what non-permissible values are. Whenever you use a rational expression, you must identify any values that must be excluded or are considered non-permissible values. So we're going to abbreviate non-permissible values as NPV. And non-permissible values are all values that make the denominator 0, okay? And those values that make the denominator equal to 0 are considered non-permissible because you cannot divide by a negative number, okay? If you recall from your past math classes, that's because when 0 is in the denominator, the expression is undefined. So dividing by 0 makes the expression undefined. So we're going to take a look at some examples and determine what their non-permissible values are. So for each rational expression, determine all non-permissible values. So we're going to start with 5t over 4sr squared. So what we're concerned with is the denominator. We have two variables in the denominator. We have s and we have r. So we can start by saying that s can't be 0 and continue by saying that r squared cannot be equal to 0. And we can simplify this expression r squared cannot be equal to 0 to r cannot be equal to 0. And we can test out whether this is true or not, whether s can't be 0, whether r can't be 0. So let's test it out by substituting in s is 0 into our original expression. So we're going to have 5t over 4 times 0 times r squared, and 4 times 0 is 0, 0 times r squared is 0, so you are left with 5t over 0, which we know is undefined. And so we say that the non-permissible value is 0. Okay, in other words, s cannot be equal to 0 and r cannot be equal to 0. Okay, let's take a look at b. We have 3x over x times 2x minus 3. So our denominator is made up of a monomial and a binomial. We can start by saying that x can't be equal to 0. And then we want to take our 2x minus 3 and we want to find out what x is in order for the expression to be equal to 0, because we can't have a value for x that would make the denominator 0. So we're going to solve for x. So we're going to bring the negative 3 over to the other side. It becomes positive. 0 plus 3 is 3. We're going to divide both sides by 2, and we find out that x cannot be equal to 0, or sorry, 3 over 2. So we have two non-permissible values here. Okay, our non-permissible value is that x cannot be equal to 0 and 3 over 2. In our third example, we are going to need to factor the denominator. Okay, so on this one we want to factor the denominator because we need to know what our factors are. And so I'll just leave the numerator the way it is. In the denominator then, a trinomial will factor into two binomials. The square root of p squared is p, so we put a p in front of both brackets, and the factors of 12 that will give me a 1 are 4 and 3. I want to make sure that the 4 is negative and the 3 is positive. So I have two factors. One of them is p minus 4 and the other one is p plus 3. And so I'm going to find out where p is equal to 0. On the first one, p minus 4 can't be 0, so p cannot be equal to 4. On the second one, p plus 3 cannot be equal to 0, so p cannot be equal to negative 3. And so my non-permissible value is that p cannot be equal to negative 3 and 4. Okay, so that ends our discussion on non-permissible values.
We're going to continue our discussion on rational expressions by taking a look at equivalent rational expressions. Now, if you recall, with fractions, if you have a fraction like, let's say, 1 over 2, we can say that that is equal to 2 over 4, and we can say that that is equal to 3 over 6. And we know that because 3 over 6 and 2 over 4 both reduce to 1 over 2. And we say that all of these expressions are equivalent because they're all equal to each other. If you were to work out the decimal form for each of these numbers, it would all be 0.5. So we're going to take a look at equivalent rational expressions. It's the same idea as these fractions, okay, where 1/2 equals 2 over 4, which equals 3 over 6. So we're going to take a look at how we can create an equivalent expression. So you can multiply or divide a rational expression by 1 and not change its value, right? Because if you multiply by 1 or you divide by 1, you're not changing the value of anything. You will create an equivalent expression by using this property. So for example, if you multiply 7s over s minus 2, where s can't be equal to 2, by s over s, you are actually multiplying by 1, provided that s can't be 0. Okay, and what you've got here then, a few things going on. Number one, we know that s can't be equal to 2. We know that this is a non-permissible value because we know that s minus 2 cannot be equal to 0, and so therefore s cannot be equal to 2. Okay, we're going to multiply by s over s, which we know is equal to 1. Okay, so when we multiply anything by 1, we don't change its value. And we also know that in order for s over s to be a defined expression, s cannot be equal to 0. Okay, so this is also a non-permissible value. So let's take our original expression, 7s over s minus 2, multiply it by s over s, and we get 7s times s over s times s minus 2. And 7s times s is 7s squared, and we'll leave our denominator as s times s minus 2. And remember to include your non-permissible values 0 and 2. So the whole purpose of doing this is to show you that the rational expression 7s over s minus 2, where s can't be 2, is the same and equivalent to 7s squared over s times s minus 2, where s cannot be equal to 0 and 2. Okay, so in other words, 7s over s minus 2 is the same as 7s squared over s minus 2. It just so happens that this one is the reduced form of 7s squared over s times s minus 2. Okay? Now, the question here, why do you need to specify that s can't be equal to 0? Well, just what we said over here. Okay, we cannot divide by 0. Okay, and what was done to the first rational expression to get the second one? Well, if we discuss that in terms of our first illustration here, we multiplied (7s over s minus 2) by 1, which is s over s, right? Because that's equal to 1. Okay, so we can create another equivalent expression by multiplying by 1 again, but this time our 1 could be s plus 2 over s plus 2. Okay, so we can take 7s over s minus 2, where s can't be 2, multiply it by s plus 2 over s plus 2, and come up with a second equivalent expression, where this time our non-permissible values are that s cannot be plus or minus 2. And that's because if we take a look at our denominators here, we have s minus 2, which can't be 0, so s cannot be equal to 2. And we have s plus 2 cannot be equal to 0, and so s cannot be equal to negative 2. So that's where this s cannot be equal to plus or minus 2 comes from. Okay, so let's take a look at simplifying rational expressions. Okay, so how do you simplify two rational expressions? Okay, in other words, take an expression which is not simplified and write it in its simplest form. Writing a rational number in lowest terms and simplifying a rational expression involves similar steps. Okay, so if I take a fraction, for example, 9 over 12, and I want to reduce it, okay, write it in its simplest form, I can take 9 and write it as two factors, 3 and 3, and I can take 12 and write it as factors 3 and 4, and I can reduce the two 3's because 3 goes into 3 once, 3 goes into 3 once, and I'm left with 1 times 3 in the numerator and 1 times 4 in the denominator, and so we know that 9 over 12 is equivalent to 3 over 4. And this is reduced, or if you like, simplified. Okay, and we can do that with rational expressions. So let's say we've got m cubed times t over m squared times t to the 4. I can take my m cubed and write it as m squared times m, and then I can just multiply that by t. So this m squared times m times t is the same as n cubed times t. And then I can write m squared t to the 4 as m squared times t cubed. And I can do some more reducing. I know that m squared goes into m squared once, and m squared goes into m squared once. I know that t goes into t once, and t goes into t once. And so in the numerator, I am left with 1 times m times 1, which is m. And in the denominator, I'm left with 1 times t cubed, which is t cubed. And remember, write in your non-permissible values, m cannot be 0, and t cannot be 0. Okay, and we get that from here. Okay, so to simplify a rational expression, divide both the numerator and denominator by any factors that are common to the numerator and the denominator. So if we have ab over ac, we can write that as a over a times b over c, and recall that a over a is equal to 1. Okay, so this gives you 1, and so really what you have is 1 times b over c. And so AB over AC is equal to B over C, where A, B, and C are polynomial factors. So when a rational expression is in simplest form, or its lowest terms, the numerator and the denominator have no common factors other than 1. so this concludes our discussion on equivalent rational expressions. So in example 2, we're going to simplify a rational expression. Your instructions are to simplify each rational expression and then state the non-permissible values. So the first thing we're going to do is simplify, and then we will state our non-permissible values. The steps that we would take: number 1, you want to factor where possible. So in this expression, if you take a look at the numerator, you have a common factor of 3, so we're going to pull the 3 out, and we will get 3 times x minus 2. And in the denominator, you have a trinomial, which you will factor into 2 binomials. When you do that, you would get 2x plus 5 and x minus 2. Notice that you have 2 factors, one in the numerator and one in the denominator, that are equivalent to each other, so that means we can reduce them. So our second step is to reduce. So x minus 2 goes into x minus 2 once, x minus 2 goes into x minus 2 once. So in the numerator then you will get 3 times 1 is 3, and then 2x plus 5 times 1 is 2x plus 5. And the last step is non-permissible values. So we have 2 factors in our denominator. One of them is 2x plus 5, and the other one is x minus 2. So on the first one, we're going to isolate x. We bring the positive 5 over to the right. It becomes negative. Divide by 2, and so you find that x cannot be equal to negative 5 over 2. And on the second one, you're going to bring the negative 2 over. It becomes positive, and so you find that x cannot be equal to 2. And so we finish writing our answer as 3 over 2x plus 5, where x cannot equal negative 5 over 2 and 2. Okay, in our next example, we're going to take a look at 2 different approaches, which will give us the same ending result. In our first approach, we're going to use factoring of negative 1 to simplify. And in our second method, we're going to use the property of 1, which means we're going to multiply by an expression which will be equivalent to 1. Okay, so as we did on the first example A, we are going to start by factoring. There's nothing in the numerator that I can factor out, so I'm going to leave the numerator. But in the denominator, I have a difference of squares, which you know factors into a sum and difference. So you're going to get t plus 1 and t minus 1. Now, if you take a look at your numerator and this factor in your denominator, you will notice that they are almost the same. They're just different by the signs on the terms. So in the numerator, your 1 is positive, but in the denominator, your 1 is negative. In the numerator, your t is negative, but in the denominator, your t is positive. So what we want to do is we want to factor out a negative 1 from your numerator. Okay, so I'm going to do that over on the side. If I take a negative 1 out of my denominator, then I am left with negative 1 times negative 1 plus t. Now take a look at the signs of the factor in your bracket. Your 1 is negative, that matches what's in our denominator here. Your t is positive, which matches what is in our denominator here. Okay. Now you could rewrite this as negative 1 times t minus 1, because now you can see the factor looks like the factor which is in your denominator. Okay, so let's rewrite this then as negative 1, hang on, let me just, negative 1 times t minus 1. Okay, so we're going to bring that up there, over t plus 1 times t minus 1. And you can see that we have equivalent fractions now, or factors, sorry. So t minus 1 goes into t minus 1 once, t minus 1 goes into t minus 1 once. So in your numerator you have negative 1 times 1, which is negative 1, over t plus 1 times 1, which is t plus 1. So we'll go over here to do our non-permissible values. We have two factors in the denominator. One of them is t plus 1. So we will simplify, or we will isolate the t, and we get that t cannot be negative 1, and our other factor is t minus 1. Isolate the t, and t cannot be equal to positive 1. And so we finish writing our answer where t cannot equal plus or minus 1. Okay, so over here on the right, start by factoring the denominator. Realize that the numerator is the opposite or additive inverse of one of the factors in the denominator. Okay, so additive inverse means that you have two numbers or two expressions that are opposite to each other. Okay, and remember, when you add opposite numbers you get 0. Okay, so additive inverses will add to give you 0. So an example would be, let's say you've got 5 and negative 5. Those are additive inverses. Okay, they're opposites of each other. If I add them, I should get 0. So what are our additive inverses in this question? Well, our additive inverses are our numerator, which is 1 minus t, and t minus 1, which is in our denominator. So 1 minus t and t minus 1 are additive inverses. Okay, if I add them, I will get 0. 1 minus 1 is 0. Negative t plus t is 0. Okay, so when you notice that you have an additive inverse, okay, so one factor in the numerator is the additive inverse of a factor in the denominator, then you want to factor negative 1 from the numerator. Okay, and that's how you're going to deal with that. That's how you make those two factors equivalent to each other. Okay. All right, in our second example, or sorry, our second method, we're going to use the property of 1. So we're just going to take the question from B and start where we have already factored the denominator. Okay, and we happen to notice that this factor in the numerator is the additive inverse of the factor in the denominator. Okay, and so when we see that, we can apply a second method. We can multiply the expression by 1, and we're going to multiply it by negative 1 over negative 1, because negative 1 divided by negative 1 is 1. So when I multiply by that, I don't change the overall expression that I start with. Okay, so I'm going to expand the negative 1 through the numerator, but for the denominator I'm just going to pop it in front of my factors that are in the denominator. So when I expand the negative 1 over the numerator, I'm going to go negative 1 times 1 is negative 1. Negative 1 times negative t is positive t. And then I'm just going to write the denominator as negative 1 times t plus 1 over t minus 1. Okay, we usually leave the denominator in factored form, so we're not going to expand that negative 1. Okay, and then what I notice is that these two factors now, the negative t plus 1 and the t minus 1, are equivalent to each other, right? Because in both of them the 1 is negative and in both of them the t is positive. So I can reduce, so negative 1 plus t goes into negative 1 plus t once, and t minus 1 goes into t minus 1 once. And so I'm left with 1 over negative 1 times t plus 1. Now generally we don't leave the negative in the denominator, so I pop it into the numerator. Negative 1 times 1 is 1, negative 1, sorry, over t plus 1, and we already know that our non-permissible values are positive and negative 1. Okay, so we are going to factor the denominator and then ask ourselves, how are the numerator and the factor t minus 1 in the denominator related? Well, 1 minus t and t minus 1 are additive inverses. Okay, and so when you see that, your second method that you can employ are to multiply the numerator and the denominator by -1. Okay, in other words, -1 over -1. Okay, so that concludes example 2. In this next example, we're going to take a look at an example of a rational expression that has pairs of non-permissible values. The expression that we're asked to consider is 16x squared minus 9y squared over 8x minus 6y. You're going to be asked three things. A, what expression represents the non-permissible values for x? B, simplify the rational expression. And C, evaluate the expression for x equals 2.6 and y equals -1.2. And you'll be asked to show the answer using two different methods. So for A, what expression represents the non-permissible values for x? Okay, so that means we want to take this denominator. We want to make it equal to 0 because we want to find out what expression would represent the non-permissible values for x. So isolate for x, and you will get 6 over 8y, which you can reduce to 3 over 4y. Okay, so that means that x equals 3 over 4y. So what does this mean? This means that when x is equal to 3 over 4, y, the values for x and y that make this expression true, or this statement true, I should put statement, are non-permissible. Okay, so this means that when x equals 3 over 4y, the values for x and y that make this statement true are non-permissible. Okay, so how does that work? Well, let's say that we take a value for x, and I can pick any value, and I'm going to say, well, actually, let's plug in for y. I'm going to say, let's say that y equals 2. Okay, and I'm going to plug that in. So I find that x is equal to 3 over 4 times 2, which is 6 over 4, which reduces to 3 over 2. Okay, so if I write this as an ordered pair, then x is 3 over 2 and y is 2. Okay, and I can pick any value for y. Let's say y equals 3. Then I would say that x is equal to 3 over 4 times 3, which is 9 over 4. And so I would have another ordered pair, which would be 9 over 4 and 3. Okay? So what this tells us is that when, we'll take a look at our first example, when x is 3 over 2 and y is 2, our denominator is going to be equal to 0, and therefore the expression is undefined. So I will show using 3 over 2 and 2 that this is true. So I'll take a look at my denominator, which is 8x minus 6y, and I'm going to plug in 3 over 2 for x and 2 for 6, and I'm going to get 12 minus 12, which is 0. Okay, So when x is 3 over 2 and y is 2, your denominator is going to be equal to 0, and therefore the expression will be undefined. Okay? So your non-permissible value then for this expression is that x cannot be equal to 3 over 4y, because if it was, you would have 0 in the denominator and therefore an expression which is considered undefined. Okay, so let's take a look at B. You've been asked to simplify. So let's start by rewriting the question. We have 16x squared minus 9y squared over 8x minus 6y. Okay, remember your first step is to factor. So in the numerator you have a difference of squares, right? 16x squared is a perfect square. 9y squared is a perfect square. So that is going to factor into two binomials, the sum and difference. So you're going to get 4x minus 3y and 4x plus 3y over, and in your denominator you have a common factor which is 2, and you are left with 2 times 4x minus 3y. Okay, so you see that you have a common factor in the numerator and the denominator, so we will reduce that. And you're left with 1 times 4x plus 3y in the numerator, and in the denominator 2 times 1. Okay, where x cannot equal 3 over 4y, okay, because that's your non-permissible value. Okay, so on the next part, you've been asked to evaluate your expression for x equals 2.6 and y equals negative 1.2. So the first thing you want to find out is whether this is permissible. Okay, so you want to check whether you can have x equals 2.6 and y equals negative 1.2 at the same time. In other words, are they permissible? So let's start by writing that x is equal to 3 over 4y, okay, because if x is equal to 3 over 4y, it would be considered non-permissible, okay? So I'm going to plug in 2.6 for x and negative 1.2 for y, and I get that 2.6 is equal to negative 0.9, okay, and we know that that's not true. Okay, in other words, the left side does not equal the right side, okay, and so we know that these values are permissible, okay, so thus x cannot equal 3 over 4y for 2.6, and for x equals, sorry, let me just rewrite that, for x equals 2.6 and y equals negative 1.2. So the values are permissible, okay? So that means that when you substitute those two values into the denominator simultaneously, you will not get 0 in the denominator. Okay? Alright, so we're going to take a look at two methods by which we can evaluate the expression. Okay? The first one is to substitute into the original rational expression, and the second one is to substitute into the simplified rational expression. Now, because they are equivalent, they should give you the same answer. Okay? So here is your expression not simplified. And here is your expression simplified. Okay? So let's start by substituting 2.6 in for x in our original expression and negative 1.2 in for y. Okay, and that gives you 95.2 over 28, which reduces to 3.4. Okay, so when x is 2.6 and y is negative 1.2, your expression is equal to 3.4. All right, and now into our simplified expression. Okay, that gives you 6.8 over 2, which is 3.4. Okay, so the value of the expression when x equals 2.6 and y equals negative 1.2 is 3.4. Okay, and so that concludes our discussion on 6.1.